Hi everyone, welcome to another tutorial session. Welcome to some more Python programming. Um, Today our task is to revisit supervised machine learning, more specifically classification analysis in Python. And together with my students assistants, we've been developing this notebook here, tutorial number 3, which strives to walk you through a lot of the modeling steps that we've been examining in the scope of the winter lecture, Business Analytics and Data Science. We don't go into everything we did in BADS, but many, I almost dare say all, of the standard workflows that we need to go through in supervised learning we have in that notebook here. I seriously plan to not have this video as long as the others, so fingers crossed, right? In terms of what we do here, everything should be familiar. That's really nothing new. We did all of this and more in BADS, but there we used R. So I want to touch on some of these specificities when doing similar jobs in Python, what libraries we use here and how. And also, if you browse through this notebook, let me give you an overview. If you browse through this notebook here, you see there is a bunch of text, right? So I mean, I know that BADS is a while ago. Maybe you forgot a little bit of that. Maybe you did not even attend the BADS course in this winter semester, but a previous one. So anyways, it should be familiar what we're doing here. These standard workflows, how you do supervised machine learning, they should be familiar. But should you have forgotten a little bit, I hope that you'll find all you need to fresh up your supervised machine learning skills available in that notebook. Okay, so we will really are able to focus on the key bits here. I continue working with the dataset from the last tutorial from creditriskanalytics.net, the HMEQ credit scoring dataset. And remember, it was a vanilla binary type of classification problem. The variable bad is our target, giving us a binary signal whether a debtor defaulted or paid back her debt. And we have 12 independent variables that characterize the debtors and allow us to predict whether somebody with given characteristics is likely to repay her debt or not, which also is our modeling task. It's a supervised learning task. We predict a binary target variable or a binary label. And the agenda is such that, well, obviously we need to load the data and do a minimum amount of data prep. Then we'll start with the good old logit model. We revisit how to estimate the performance of the logit model, but more generally, any type of supervised model, going through some workflows like resampling, cross-validation, and also revisiting some performance indicators like the confusion matrix or receiver operating characteristics. Then we move on with regularized logit. And since regularization will always introduce at least one metaparameter that we don't estimate as part of the model building, but need to set a priori, we will look at model selection and grid search in that scope. And once we know grid search or remember how grid search work, we can move on to look at some more complicated classifiers, and we will revisit the random forest algorithm and extreme gradient boosting, see how you can access them in Python. And I'm confident that with this set of learning algorithms, logit and regularized logit, plus these two tree-based ensemble algorithms, random forest and XGB, that should really get you started with pretty much any supervised machine learning problem you might come across. We probably have the most important algorithms in here, minus the one that we do not consider, artificial neural network. Of course, there is a reason we don't consider it here. We will pretty much spend any remaining tutorial on neural networks. All right, enough of the introduction. Let's get started. We start with some standard libraries, of course, and the one that are more specific for model development, those that are new in this tutorial, I'll introduce them on the fly once we need it. So these will come later. The first part is just data integration. Basically, I'm redoing everything we covered in tutorial number 2. Should you feel a bit unsure why we are doing certain steps, just look into tutorial 2 and it will tell, okay? By the way, the steps, the thing that the way we prepare our data is almost exactly the same as in the last tutorial. So we do something about missing values, we do something about outliers, we encode our categories, everything as in tutorial 2. I try to write the code a bit nicer, a bit more elegant maybe. So I would encourage you to have a look at the code. Is there a way for me to show that? Here, for example, remember, in our data, we have 2 categorical variables. We have reason and we have job. Maybe. Oh, I think I forgot to run the previous code. Apologies. I was so eager to not waste your time that I forgot to run the previous code, which just loaded the data from disk. And I should now have access to a variable, HMEQ, which is my data set. Yeah, there we go. And here are reason and job of type object, and we need to do this preparation of these variable to bring them into a format suitable for modeling. And you'll see some lambda functions here, and you see me using apply. As I said, I was trying to write the code in a way that is maybe less clear, but more concise. So we process our 2 categories without loops, or almost without loops, using this apply function. And we use that to, first of all, convert them to the right data type, category, and to then add a new level is missing. And then, well, for the actual replacement or actual handling of missing values, I found it more convenient to use a for function. The code to squeeze that into one line just proved a bit too complicated. But that's all what we did last time. And there is one thing that is new. Let me split that here so that we can run all the above code. And maybe here we go. Maybe start with this overview. We now have these categories, reason and job. And you see the category level, some improvement. The other was depth consolidation. And we also have our new category label is missing here. Same for job. And you might remember that certain learning algorithms have issues with processing categorical data. Funnily, in Python, even many tree-based algorithms like random forest, they would not allow you to use categorical data. They would not allow you to use a category or a factor in a data set that you put into a learning algorithm. Actually, I don't know why. Obviously, it has to do with the implementation. So we really have to encode our categories. And while I don't go into weight of evidence in this tutorial, we need to do something. And what we do will be dummy coding. So the single new bit of code here is dummy coding, where we basically take all the different category levels, home improvement is missing, and depth consolidation, for example, and introduce binary columns for each of these options. Anyways, you will remember what a dummy variable is. And Python allows you to do the dummies either using pandas functionality, or it's also available in scikit-learn. I'm using pandas here, and that's really nice. So you just have to call this function getDummies, and you specify the data frame from which you want to derive these dummies. You can specify a a prefix separator that has to do with the way the new dummy variables are named. You'll see that in a second. You need to specify which columns you want to process here, where I'm just having my list of categorical variables that I created earlier on. And the last bit here is important. Do you want, for a category with n levels, do you want to create n dummies or n-1 dummies? And that's called drop first here. Drop first means you just remove one category level, and that is what you must do for any sort of regression model, because otherwise the variables that you create are linearly dependent on one another, and that will impede your regression model, and you will get biased estimates of the regression coefficients, if any, depending on how the estimation works. Linear dependency among the variables might even crush the estimation. Okay, so it's a one-liner, which is nice, just one line of code, and we get our dummies. Let me show you this. Instead of reason and job, I now find a bunch of new variables in my data. If I use the info function, reason underscore home improvement, that's this symbol of separation, and reason underscore is missing. It's a little bit annoying that I could drop the first level, right? That's this bit here. I have this argument, drop first, which is convenient, but it will drop the first level. And turns out that the first level that is dropped here is the category depth consolidation. I didn't really look into too much detail how this first category level is determined, but you see here that out of the three levels that exist, depth consolidation, home improvement, and is missing, only home improvement and is missing survived the dummy coding. And that's maybe a little bit annoying, because probably you would not want to have this is missing label, but rather would like to have a dummy for the other actual category level depth consolidation. Of course, you can achieve that, but it's more effort, so I was a bit lazy here. But you do see all these dummies, and obviously we could also take a look at our data and how it looks by now. And then if we scroll a little bit, here are all our nice dummies. Home improvement and is missing, there they are, right? That was easy. And that's pretty much it with the categories. Everything else we covered in tutorial 2, so let's move on with the numbers. And some repetition also here, missing values. Replacing these as before using the median. Outliers, yeah, as before we do an interquartile range based truncation of outliers. Well, what we do is not new. We just do the outlier truncation. I actually spent a little bit of time to try and write that up in a nice way. So please have a look at the code and the way this is done. I'm using a lot of indexing here. First, getting me an index of all the numeric variables in my data frame using list comprehension. That's not new. Then we are creating a little data frame here by applying the quantile function. We did that last tutorial, but not for the whole data frame or a subset of the variables at once. So that's quite nice. I specify the quantiles I want to see, which are the first and the third quartile, and then applying that to the subset of columns using this index here, I get a new data frame that gives me the first and the third quartile for all the numeric variables. Okay, and then based on that data frame, there is a function diff, which is meant for time for series, for Panda series. It allows you to calculate the difference between the rows in a series. That's very useful for time series analysis, but we could also make use of that to calculate the difference between the third and the first quarter. So this way we obtain the interquartile range for all the variables just using this. Well, some more pandas handling here to make sure that I don't get into issues with the row indices. Note that the row indices here, after using quantile, are 0.25 and 0.75. That's a bit odd. These are row indices. You might wonder why is that? It's just the default behavior here. But more importantly, if you look at that data frame, Q, and say you want to index Q, say you want to have only the values corresponding to the first quartile, okay? So you want to extract these 11,100 here, these 48,000 something, etc. Using standard indexing, the data frame, the variable is called Q, okay? Using just ordinary indexing, as I introduced it last time, you would maybe do something like that. You could go log, and then you might be tempted to say, well, I want the first row. So remembering that Python starts indexing at 0, I go log 0. And then all the columns, I could just do it like that. And that's pretty nice, looks pretty okay, but doesn't work. And well, you might wonder, why is that not working? That's weird, really. And it has to do with the indexing. In this data frame, the row index is not just a consecutive set of numbers. The rows are not indexed from 1 to n, n being the number of rows. The row index is now these numbers here, 0.22 and 0.75. Not 0.22, that's nonsense, 25, sorry about that. And because of that, if I want to index this guy here, I have to use this 0.22 as a row label. And that's a bit bizarre. Makes total sense. If that is my row index, well, I do indexing by specifying the indices of the row I want to extract, right? So it does make sense, but it's a bit, a bit awkward still. Feels a bit awkward, at least to me. So when you see a little bit of code here and aren't really sure what this code is meant to do, debug it, test all the rows one by one, check what's happening to your data frame. I'm basically cleaning up these indexing here a little bit. To get this, that is the interquartile range. Again, it's a data frame. And here I basically have my row index as a nice number starting with 0, what we are used to. And then we can basically do the whole outlier replacement in this bit of code here. In one for loop, we take care of all the columns. And I'm a bit more modest here and have used a factor of 3 to indicate my outlier. Okay, I'm delving too much here into this code. Have a look at it. The same we did before, but written up in a nicer and hopefully more professional way. Okay, let's run that. And now we are done with cleaning our data frame. So missing values, we did that on the way. No missings anymore. Outlier truncation, done with that. Category coding, done with that as well. We even did the dummy coding. Last thing, we have these numeric variables that are unscaled in their raw value ranges, which are monetary figures, but they differ quite a lot. And what we typically do is we scale our numeric variables before putting them into the model. And depending how far you went in the lecture, you might know already that scaling the data is crucial whenever you use neural networks, because you don't want to run into the saturation level of your activation function. And if that sounds like nonsense or does not make sense to you, no worries. Probably you just have not arrived at the corresponding part in the lecture with activation function bit. Well, we cover that in the foundations of neural network. Well, thinking about it, foundation of neural network is the second chapter, so probably you know what I was talking about. Anyways, if you want to scale your data, you know about the different options. You can do min-max scaling. You can use the Z transformation, which is what I'm using here. There is this class, scikit-learn, or there is a collection of scaling classes which you find in pre-processing. I'm using the standard scaler here. That's one class that implements the scaling by calculating the Z transformation. You scale a variable by subtracting its mean and dividing by the standard deviation. And if you want to use a different form of scaling, if you want to do min-max scaling, for instance, where you subtract the minimum and divide by the range to scale a variable, you just use a different scaling class from that namespace. That's nice. And all these classes, the way to use them is exactly the same. I'm using a convenience functions fit and transform. I'm extracting all the numeric variables using select d types. That's known by now. Then I fit my scalar and at the same time transform my data using the fitted scalar. You can do that in steps. There is a function fit and there is a function transform and some more. You can do that in steps, but there is this convenient function fit and transform because this is a common use case. Fit here means that to calculate the Z transformation, it's again subtracting the mean, dividing by the standard deviation. And fitting means you need to calculate the mean and the standard deviation because otherwise you can't do the scaling, right? That is somewhat similar to fitting a model, and that you determine parameters that you need to know in order to run it. For regression, you need to know the values of your regression coefficients. Then you can apply your model. Same with scaling. For that transformation, you need to know the mean and the standard deviation, and that you get with fit. And then transform means you apply the statistics in order to alter the variable values in some data frame. And fit transform does that in one go. So I have x new here, and then some conversion from arrays to matrices, and eventually overriding the numeric columns in my data frame using their scale diversion. And running that gives us a new data frame, and now we are ready to start with the modeling. Here you see this number ranges might not make immediate sense to you, but if you look closely, you'll notice that we have smaller negative numbers and positive numbers as well, and they are all sort of in the range -1 +1, which does make sense. Well, this one is a little larger here, which does make sense, this range, because standard scaling means we map everything to a standard normally distributed variable. That was it. Now that's a little bit inaccurate, but if the variable beforehand was normally distributed, then we would expect that the corresponding z-score of a variable should normally be around 0, and then with 66% probability, roughly between +1 and -1, and so far. So that value here is already quite large for a standard normal distributed variable. We know that our variables are not normally distributed. We've seen that last time when looking at the histograms. But well, for today, this type of scaling is enough. The number ranges, the numeric ranges of all of the variables are reasonably similar so that we can compare regression coefficients across variables. Standard scaling is enough for us. And the data is ready. Same code as last time, just to double check how our distributions look like. And well, going through this bunch of histograms here, it's absolutely obvious that we could do more and probably should do more if we want to optimize our data preparation to get really strong models out of it. Then there are a couple of issues remaining with that data. Some of the dummies look rather imbalanced. That guy here, reason is missing. Looking at that distribution, I don't need that dummy, right? The number of ones is so tiny that there can't be a lot of signal in that variable. I can probably kick it out. And what else? Here, that guy as well. That's a numeric variable, but looking at these values here, I would probably turn that into a category instead of leaving it as a number, because the distribution is really left skewed, and a category appears more suitable for that type of variable here. But we don't want to take it that far. Rather, we want to proceed with building some models. And in scikit-learn, the standard way to call functions is that you put in a response variable, a target variable, a label, and the independent variables. Because of that, to make my code more readable, I'm creating these two variables here, y and x, which basically is the vector of all the labels and the matrix of all the data, but the label. So note that I remove the column bed from my data frame, and the result I call x. So now I have x and y. I have done some pre-processing. We can do some modeling, starting with the logit model, which you hopefully remember. A little bit of explanation here, but this is only meant to, well, remind you what logit is. And if you go through that and everything comes back fine, if you afterwards still feel you're not really sure about logistic regression, please have a look at it, because it's really important. But that shouldn't be the case. If you run logistic regression in Python, unlike R, you need to be aware of the purpose that you have in mind for this logit model, because logistic regression is popular for both building explanatory models to study the relationship between x and y, and also in predictive analytics, where our main concern is to get good forecasts of y from x. But in Python, there are multiple versions of the logit model in different libraries, and I'm starting with the stats models API, which supports logistic regression through its function logit, importing that library using the function logit, calling that with my freshly created variables y and x, get my logit model, not really the model, but an object. That's object-oriented programming. I'm getting this object, which is sort of ready to be used, but it's not yet estimated. To estimate my model, I need to call the method fit on that object, where the object also has this data stored in its properties. And then I can look at the results of my logit model. And you already see the result. That looks very much like a standard regression type of plot or output, where we have an R-square, well, pseudo R-square because it's a logit model, and we have likelihoods, and we have a p-value for the log likelihood ratio test, and we have our nice table with the estimated regression coefficient and their standard errors, a p-value indicating that the vast majority of these variables is actually significant. Here's one exception, which is reason is missing. We saw that earlier on in the histogram, didn't we? That's the only insignificant variable. And indeed, yeah, Let me go back. That last one here, that is reason is missing. If you look at that distribution, of course, the variable is not significant in the model. How could it be with that distribution here, right? That's a nonsense variable. I just didn't bother to kick it out. So this is what you would expect when running a regression model. And for some reason, you don't really get these results, definitely not that easily, if you use the other implementation of logistic regression in Python, which is available in the scikit-learn library, the go-to library for machine learning. It has a model for logistic, or it has logistic regression, and it's actually a very nice implementation of logistic regression, powerful, efficient, crunch big data sets, but you can't easily get this standard table to my knowledge. And therefore, you want to know that logistic regression is also available in the stats model API. And that's the API to use when doing explanatory modeling. It's not as efficient, but I would expect that if you find yourself in an explanatory modeling setting, your data won't be that big. All right. That was our first model estimated. And the next thing is to assess models. And you know how to assess models by using holdout data for assessment. I hope you know that. Again, a little bit of information I provide, but you should know that. And again, scikit-learn comes in useful here. There is another namespace that you have to remember. It's the namespace on model selection. Well, I call that a namespace. And from that, we import the function train test split, which is a split sample setup. And then we just use that function here, apply that to our data x and y, telling the function how much test data we want as a percentage. And as a result, we get these four outputs. That's maybe a speciality in Python I might better comment on. Yeah, a function can have multiple return values. Normally, you think of a function as returning one result. And in a way, this is also true for this train test split function or any function. But the result that this function returns is a tuple, what Python calls a tuple. It's this data structure where you have a set of atomar type of variables. And I can basically take these elements in this tuple apart when calling the function like that. So the first element in the tuple that train test split returns will end up in my first variable here, xtrain. And the second element that is returned in that tuple is then part of xtest and so forth. Well, you'll get to see this type of syntax very often, where you call the function and then pull multiple results from that function. Python, that's normal. If you are new to Python, that might look a bit unfamiliar. So just note that this is quite standard. And using shape that you know well, you can get the dimensionality of the resulting data that shows you how we now have close to 5,000 observations in our training data and a little more than 1,000 in our testing data. Okay, now let's repeat the estimation of logistic regression. And in the second example, I'm using the logistic regression model from scikit-learn. I'm importing that from the namespace linear model. The syntax is also a little different. You have to specify whether you want to use a penalty, that is a regularization penalty, and only if you say none, you really build a logistic regression model as opposed to a regularized logistic regression model. Earlier versions of scikit-learn were only able to give you regularized logit models, but not the ordinary one. What else? Fit intercept. Yeah, we typically want to have an intercept. The number of iterations for the algorithm that estimates this model. And then once more, that's typical. First, we create the object by calling the constructor. OOP folks call that the constructor. We construct an object of the class logistic regression, specifying some parameters. Then we have our object. And for that object, we can call the method fit, which does the estimation for us. So that is also the method that might take a while if we have a lot of data and a complex model. And then we can print out the result. You already see them here below. Let me run that. There we are. And if I print the result of my model, although this is a logit model, what I get as a result is just this type of summary of the class and the parameter values. Or an OOP person might call that the values of the properties of that class. But definitely not the regression table. And I'm also extracting some performance statistics. Classification accuracy is very easy to get. Every modeling class offers you a score function. I'm using that score function here, and that gives you basically the classification accuracy for the data that you put in. And I do that for train and for test to check whether there is any indication for overfitting, but apparently there is not. In fact, these numbers look so similar that I wonder whether my code is correct, but yeah, I'm calling score once for the training and then for the test data, so that should be correct. Let me do that once more. Yeah, by calling the train test split one more time, the random partitioning of the data into 20% test and 80% training is shuffled or is done differently. And therefore, I get a different result when calling this another time. So if I just call this cell one more time, I would expect seeing the same numbers, 0.83 and 0.8406, and there they are. Because the estimation of the logit model, that should not entail any stochasticity. So only if I redo the terrain test splitting, I should see different numbers. One more time, one more. So novel train and test set, not in size, and again, different numbers. If you write production code, you want to control the random number generation that governs how your data is split and is partitioned. Didn't bother with doing that, but for production code or also for code that you write for a thesis or for your assignment, for example, you want to ensure that your calculations are replicable. And that is why you need to control the seed of the random number generation. And that is why by not doing it here, anytime I redo my data splitting, I will get a different result. However, the overall tendency in all these results is that there is not much difference between train and test set performance, which is good news. The model does not seem to overfit. There we are. More generally, performance assessment, there are a bunch of measures, as you might remember, and classification accuracy, which is very easy to get, but that measure is one you probably don't want to pay too much attention to because of its dependence on the classification cutoff, and that is why we typically prefer to use ROC analysis. Before doing ROC analysis, I wanted to show you some ways to get a nice confusion table out of your classifier, even if I'm critical with threshold-based performance measures like classification accuracy. The confusion table is still useful at times, and the quick and dirty way to get that is to just use the method confusion matrix, which is part of the metrics family from scikit-learn. So again, you need to import some functionality, and then you get these functions. In later tutorials, we will basically just have a block of code in the beginning of the tutorial where we load all the libraries that we need. That's also the way that the Python guideline recommends us to proceed. But to illustrate where to find the functions that I'm introducing, I'm deviating from that guideline and always import functionality upon its first occurrence in the code. Okay, confusion matrix, that gives me, well, essentially this NumPy array, where it's a bit hard to make sense of that. And you should know the function plot confusion matrix if you are interested in confusion matrices, which if you call that with your model and the test data and then maybe some other parameters for pretty printing, like what are the labels, gives you, oops, I probably forgot to run some previous code. Indeed, I did not import the metrics library. Now, there we are. So that looks a lot better and is far easier to interpret because we see right away what are our true labels, what are our predictions, what are the true positives and the true negatives, and how many cases end up in which of these four cells. So it emphasizes that our classifier is pretty good. We do see the majority of the elements in the main diagonal, obviously because accuracy was above 80%. However, we also note that the logistic regression has a tendency to predict good way too often, where actually a client would be of class bad. And remember that in credit scoring, predicting somebody who's actually bad as a good, that is the costly error, because that means that you would give this person whom you expect to be a good risk some money, you would lend money, and in the end, that money would not come back because in reality, that's a bad risk. So that's probably alarming to see a model that is prone to this false negative error. If assuming that good is a negative class, then this is a false negative error because we predict negative class and it's false. And since our classifier predictions are all continuous and represent probabilities, this matrix is based on the classification cutoff. And ROC analysis basically is the generalization of the confusion matrix where we consider all the possible cutoffs from 0 to 1. And again, there is a convenience function that we can make use of in this namespace matrix, which is plot ROC curve. I'm putting in log, which is the object of my logistic regression. I'm also putting in the test data, and then I get my ROC curve. I do, however, have to manually add the random baseline, the main diagonal. That's not part of the scikit-learn ROC curve by default, but it's easily added, as you see. And there is our logistic regression ROC curve. AUC almost 0.8, so pretty good model. But I'll tell you, we'll do better than that. If you want a little more control about your ROC curve, then this function, which does everything for you, as convenient as it is, probably not the one you want to use. For instance, if you want to have multiple ROC curves in one plot, then it is better to create this plot manually. And let's do so. Here is the code. If you create your ROC curve manually, then the first thing you need is the classifier predictions. And I was saying earlier on, these predictions are probabilities, normally, always in our use case. When we work with neural networks, well, we will have softmax layers, and we will always work with probabilistic forecasts. So here we go. That is the way, and we haven't seen that before because we were using only these convenience functions that hide the calculation of predictions. Here we see for the first time how to calculate predictions, and every scikit-learn object would allow you to produce predictions using the function predict. That is available for every object, predict, and then if I put in some data like xtest, the result that I get is an array, and this array obviously is of data type Boolean because my label is stored as a Boolean. If you have a classification model and you call predict, then predict will give you class predictions, something discrete, which is great if you want to construct a confusion matrix, but if you want to do a ROC curve, that does not get you there. And this is why there is also a function predict probar, which gives you the probabilities. And predict probar, again, for a reason I'm not too sure of, gives you both the estimated probability for the negative and the positive class in a binary setting. And you could ask, what's the point? One is just one minus the other, and normally you want and need only one of them. Still, predict probar will give you this two-dimensional array, this n by 2 matrix, and then you always need to take care of that manually and just index it in order to get the estimated class probability for the positive class, which is the second dimension. That actually gives some room for confusion. Do I really get out the right class here? But well, it should not be too difficult to find out which one, which class is which. And if your label is binary and encoded as a Boolean or with integer values 0 and 1, then the second column is the one you want to use. Okay, so that's the first step. We extract that probability here, and then we put that into the function ROC curve, which is, if you wish, a lower level function that gives you the data for the ROC curve in the form of the false positive rate and the true positive rate. And I'm doing that twice, one for the test set and one for the training set. And my use case here is to have a ROC curve with both these results. So that's basically all I wanted to show you here. There is this function ROC curve that you can use. It gives you the underlying data for your plot, and then you can do the plot. And well, the plotting is not so super interesting. It's just a line plot essentially. And I'm just using matplotlib here to do this plot, adding some labels. And then in the end, here's the graph of our ROC curve with train and test set performance, where we can compare both sets to check whether there is evidence of overfitting, which there isn't. In fact, my test set score is a little higher than the train set score. That's just random variation. And also these curves are pretty close by another. Okay, there we are. And from now on, I will trace my performance for every model that we build. I'll just put the test set AUC into a dictionary so that later on I can do some comparison. That's the purpose of this bit of code here, where I'm creating this dictionary, which for now has a single key, which is logit, and then we'll append that as we go along. You also have a little cross-validation demo here. Well, just skip through that. There is another function in the model selection namespace to do cross-validation. The way I'm using that is, well, fairly manual. I could make use of a bunch of functions that are implemented to make cross-validation easy for you. For example, with one line of code, you can get a cross-validated AOC score. Well, just for fun, I'm considering a use case where I want to manually build a ROC plot with different curves for different CV iterations. And this is why the code is a bit lengthy here, but essentially it's just here using a function stratified k-fold, which does the data organization for me. I'm asking that function to give me 10 cross-validation folds. And then I would write a loop which runs over these folds, that's the lower part here, where I basically extract the training and validation data for my 10 cross-validation iterations. So it's really a manual cross-validation just so that you have seen it once. And everything else is really about getting the data for the ROC curve and preparing the plot, also printing some output here. What are the AUC scores for an individual iteration? And then here's my, oh, that's a bit overwhelming, my big plot in the end with all the different ROC curves. It helps you to get a feeling for the variation of your model over different cross-validation runs. And that was it. Let's look into regularized logit, covering our second algorithm. Remember that in regularized logit, or generally in regularized models, the idea is to change the objective of model estimation from optimizing fit or minimizing loss only to minimizing loss plus minimizing complexity. And it's very typical that we have this part in our objective that in one way or the other captures the complexity of the model. And this bit here should look familiar. In a regression model, complexity is captured by the magnitude of my coefficients. And then we can look at the L1 norm or the L2 norm over all the model coefficients. That's L1. And the resulting model is then called lasso. That's lasso regularization. With L2, it would be rich regression. And we have this lambda guy here, which is the meta parameter to control how much I want to emphasize the loss minimization part, the first part here, during model estimation, and how much I want to concentrate on minimizing model complexity. And building a lasso model is really easy with scikit-learn. You just use the same function as before, logistic regression. This time, however, you don't say penalty equal to none, as I did before. You just specify what type of penalty you want to use. And L1 ensures that you get a lasso model in the end. You can also look into the documentation to check what is available. So apparently, the default penalty is a L2 rich. But if you scroll through the documentation, here we go. So we have L1, we have L2, we have more than that. We also have ElasticNet. So basically, all the common penalties you've got. Using this scikit-learn function logistic regression, you can estimate a vanilla logit model minus a statistical test. You can get a lasso or ridge model, or you can do elastic nets, regularization. So basically all you need in one function. That's the big advantage. But again, it's wonderful for predictive modeling, for explanatory modeling. You don't want to use the scikit-learn logit model, but go for stats models instead. Okay, let me just run it for completeness. Since we need to specify the weight for our penalty, the lambda, we just encountered our first meta parameter. The argument is called C in the logistic regression function. Well, that doesn't really matter. We have our first meta parameter. We need to put in something. We need to specify how much weight we want to put on having a model that's not complex. And normally we just don't know what is a good setting for these meta parameters. So on with grid search and model selection. Obviously, you have functions to do model selection. And while being pretty much infeasible for neural networks, for vanilla machine learning algorithms like logit, grid search should do the job. You have the function grid search as part of the model selection family. And with this function, you specify a dictionary of parameters and candidate values. So note I'm specifying this bunch of values, candidate values for this parameter lambda or C, the regularization penalty. And then you just call grid search, specifically grid search CV. So I'm doing grid search using cross-validation. If that rings an alarm bell and you're now wondering, oh, isn't that costly? Yes, it is. You could also have grid search using only split validation. But the standard way to do it is grid search CV if you can afford that. What model? That's just our lasso, the object we created earlier on. It's all nicely object-oriented here. Well, I shouldn't say that, because if it were nicely object-oriented, I couldn't make use of the function grid search. We give our dictionary penalty setting. We tell our function which is the performance metric we want to optimize. Luckily, ROC is available. MSE is also available. Classification accuracy is available. If you want a grid search over some more exotic metric, lift, profit, that might not be available, so you could not make use of that argument. You might have to first extend the functionality of grid search CV so that it knows your objective. Say you want to optimize for profit, you must basically implement a profit function, make that known to grid search CV, and then you can use it. There are tons of resources, examples on the web, so it's possible. It's just not as easy as just specifying one argument. And then I'm telling the function that once it has found the optimal parameter values, it should refit the model on the whole data. What's the whole data? Well, we use cross-validation to assess candidate settings for the regularization penalty. So we split our data, have less data for training because we need to hold back something for validation. Once I found the optimal parameter or penalty, lambda, I can re-estimate my model on all the data, the entire training set for that lambda. And that's this parameter do refit equal to true here. I should have run the model meanwhile, but luckily that's pretty quick here. It's still running, but here we go. So we already moved our AUC before we had a value of 0.79, if you remember, and we are already at 82, from 79 to 82 using lasso and grid search, so getting there. And if you're interested, there are ways, obviously, to find out what was the best metaparameter setting. Once you run the grid search, here, gslasso.fit, again, invoking the fit method, then afterwards I have access to this property here, best params, which just gives me the optimal metaparameter values, meaning those that delivered the highest score, ROC score in my example, during the grid search, during cross-validating all the candidate parameter settings. Okay. Oh dear. I shouldn't admit mistake in my video, but I think there was a typo. Well, to be honest, I think there were many typos in this tutorial because I really, it's freshly baked for you in this semester to provide a lot more explanation than what we did before. Yeah, but I didn't proofread anything. Sorry about that. Next on the list, random forest. You have a couple of metaparameters that you could tune. I'm listing them here in the description. But the ones that you typically want to tune are the ensemble size, the number of trees in the forest, and that parameter is called an estimator. Sorry about that. That's an estimator. Ah, shoot. Oh my goodness. And you also have the number of features that are sampled at random for every split in a tree, which scikit-learn calls max features. That's what, well, I usually refer to mtry as mtry. Many more metaparameters. Look into the documentation if interested. Typically, tuning these two in a random forest is enough. One parameter you want to have on your list, you can control the size of the bootstrap sample for every tree. Let me run the code because it's going to take a while. This metaparameter max samples allows you to tell the random forest how large is my bootstrap sample, and that is the mechanism that you should use to accelerate training if you need to. Don't reduce the number of trees. I hope you will remember why that is a bad idea. Rather, reduce the number of data points on which you train. Okay, so let's have a quick look at the code. Scikit-learn.ensemble have many algorithms just waiting for you to be explored. We use the random forest classifier. And then again, I'm creating an object of type random forest, invoking this constructor. It's a random forest. If you want replicability, then you must set the random state to some seed value so that you always get the same sequence of random numbers, and that translates into always getting the same bootstrap samples when you run this method multiple times. And here you see how I set max samples to 0.5, which says that if my training set has 100 observations, draw me a bootstrap sample with replacement of 50 observations, and then grow a tree from that bootstrap sample. By default, that would be the same size as the training data set. And clearly that's a good idea. More data is better, but I didn't want this to run too long. What else? Again, I'm using a dictionary here to specify the metaparameters I want to tune. And you have to make sure that you really use exactly the name of the metaparameter that the random forest classifier knows. And then as values in your dictionary, you put the candidate setting. So you see how I consider trees of size, forests of size 100, 200, and 500, and how I consider the settings of 1 and 2 and 4 for random subspace. It's maybe a bit confusing that the names of these parameters don't match with their names in, well, in R or also in my explanations. Not sure how they came up with these names. To me, everybody would call that mtry, but obviously I'm also subjective. So we just have to look into the documentation from every now and then and make sure we know what some metaparameter really is referring to. And then this is the nice part. It's a lot at the beginning, I know. If you haven't done it before, it's a lot. But you should, well, at least you should know the concepts. And then this code, if you compare grid search for lasso and grid search for random forest, you will notice it's basically the same. It's the same syntax, it's the same programming statements. The only change, I put in a different object because I want to grid search different classifier. I put in a different parameter grid because random forest knows different metaparameters than lasso. And that's pretty much it. I again have my scoring functions that is optimized. Here I'm using cross-validation false only 5 because I'm a little bit alert about runtime. And that's it. Calling fit, done. Giving the training data and the training labels, and that's it. You wait a little bit, and then you get your optimal parameter values. I'm printing these out. Let's have a look. In total, we have fit 45 random forest, 5-fold for each of the 9 candidate parameters. That makes sense. It took us 1 minute. You see this output here. Scikit-learn would make it easy to parallelize the computations. I didn't bother. And also my laptop wouldn't really give me a very large speeder because I don't have that many cores here on this machine. But just in case you wonder about this output, grid search natively supports parallel computing. And bah, look at that. Best AUC 0.978, that's close to perfect. It's a really powerful model. And in fact, it's the one, that's maybe a little bit odd, max features equal to 1. And you might say, so what? But if you really follow it along carefully, you will know that that means mtry equal to 1. So random subspace, you pick one feature. That's very tiny. Bit surprising that this setting turned out to be the best. But then our data is rather low dimensional. Maybe it's related to that. Anyways, we get a beautiful AUC score and have an almost perfect model. Due to that, you might want to do the ROC curve again, and it will also look at that ROC curve. That's why I picked the data set. There is a very strong signal in the data set. As a matter of fact, the data set is a bit massaged to have that strong signal. And that is nice that we really get good results when working with complex models. That's not always the case when working with real-life data, as you know from your batch experience. Okay, in the reminder, you just have exactly the same code one more time, but for XGB. I'll run it, but can almost go over that. As with MLR, this package we used in the scope of batch for R, you just import a different learner. You set the parameter grid, and then you call grid search. So it's super easy to have many algorithms and consider many algorithms because the design of the whole scikit-learn framework is very much thought through, and yeah, once you have gained a little bit experience with that, you'll really be very fine. Note that for XGB, which is maybe the most well, popular / powerful off-the-shelf learner there is. You typically can do a little better than random forest if you tune your XGB carefully. There are multiple implementations available, one in scikit-learn. Well, okay, I haven't checked that in detail. I think the scikit-learn version is actually GBM. Not exactly sure. There is an XGB version available. And in any case, I think if there is, you would not have the full set of features of XGB. Anyways, the version I picked here, that's the one you probably want to use, XGBoost. And that version, interestingly, is not part of Anaconda. So probably when you want to run that notebook, you might have to install this package on your own. That's probably the first package that you might need to install on your own if you use Anaconda. It might have also to do with the different versions of Anaconda and which one you use. Maybe it's already part, but note that should you get an error saying something like XGB not available, that's probably because you didn't install it. So make sure to install that library. Or you can update this code and use the scikit-learn implementation of gradient boosting. That would be fine as well. Okay, the rest is just the same. Here we are having 200 trees in total. I'm considering a bunch of parameters, the random subspace parameter again, and here it's called call sample by tree. That's mtry once more, the number of trees, the number of boosting iterations, that's n estimators, the maximum depth of my decision trees, the learning rate, it's gradient descent based boosting. So we have a learning rate, early stopping. What's the best set of parameters? So mtry equal to 0.5, call sample by tree, but I can't help and call that mtry. 100 boosting iterations, depth of only 10. I think this is the shallower version. No, it's in fact the deeper version. Oh, that's interesting. It's the deeper version, maybe because I don't have that many iterations. And, well, also very high, not as high, interestingly, as random forest, but very high AUC score. And that's it. We have seen a bunch of models. And, well, the main take-home here is that the way you use these models is very similar. Pretty much always the same type of code. You just change one object for another. If you do tuning, you change your parameter grid one for another, and that is it, really. So using scikit-learn is really nice once you got into it, and I hope that with this tutorial you have code examples that get you started. I hope the notebook is useful for you, and eventually you'll find it to be useful. I think my XGB is still running. Yeah, my XGB is still running. We definitely want to have a look at the final prediction results. But that will take a little longer. Okay, so we just be patient. Meanwhile, in the reminder of this tutorial, I thought it might be useful to briefly touch on model diagnosis. In this example, I did some cherry picking with the data, right? But here we really have this tendency that nonlinear models, black box models, do better than simpler linear models, a lot better, in fact. And hence, you would want to use these black box models. And the question then is, what really is the type of relationship they have picked up? And we had a lecture on that in business analytics, and two popular techniques in order to gain some insight of what a random forest or an XGB model does internally are permutation-based feature importance and PDPs. So the last bit of the tutorial presents you some code, how you can use the Python package scikit-learn inspection. The scikit-learn is really the single one library that has everything, including techniques for IML, interpretable machine learning. And for start, I'm using the permutation-based importance scores. That was this approach where you take your data, corrupt one variable by permuting the values. So all the actually old customer might get a new age value, and out of a sudden there are young customers. Through permuting the variable values in one variable, you break the relationship between that variable and the target. And then you calculate some predictions with your model before and after permuting a variable. And because the permutation breaks the feature to target relationship, you expect that performance after permutation is worse than before with the original variable. And the more performance decreases, the more important was the variable and the more harmful was permuting that variable. That's the idea of permutation-based importance. And that works with any type of algorithm. You can apply that to regression-based techniques, even if they are interpretable, but it works with every type of algorithm. The code is, yeah, it's again a bit mechanical. We have a function. We can call that function, what we do here. We need to understand the way this function likes its arguments being specified, but it's not a miracle really. It's no magic. We give it one trained classifier, and I'm using a random forest because it does best on this data. We give it the test set, specify our scoring rule again. It's about permutation-based feature importance. It's about the decrease in performance before and after permuting a variable. What is performance? You can tell what performance is, and I'm using AUC performance. And then that's some code that you can do it in a more concise version. You can do it a bit more easily, these permutation-based scores, but running that code with a little bit of overhead to get a nice graph is useful, I believe. And then look at that analysis here. It takes a little while to produce that graph, so I don't rerun it. I have pre-computed that. I think my model is already, my notebook is still busy with the XGB. And you can then get these permutation-based scores where you find which variable is most important. And indeed, it is a beautiful data set for teaching. Not only do we get very good AUC, also the insight we gain makes a lot of sense. The most important, the single most important variable is debt to income. And for a banker, that's a no-brainer, how that is the most important variable in our data set. The number of delinquent credit lines also turns out to be very important, which makes so much sense. The age of the oldest credit line of that customer turns out to be important. These are the three most important variables, and we can compare them. We can also judge whether job is missing, reason is missing. We also see those where basically permutation does not seem to change our RUC performance, AUC performance, that these you could get rid of. So it's also a way to identify variables to be discarded in another round of modeling. So quite a useful analysis. And it's easy enough to produce this graph. But it's the vast majority of the code is really to do the plot. All that bit here is just the plotting. Have a look at that. And getting the feature important is basically a one-liner, as usual. Before moving on to PDPs, let's have a quick look because our XGB has finished and I'm still short on reporting the overall AUC results. Here they are. We had logit, we had cross-validated logit, which on average was a little weaker than logit. That just shows how a single test set is prone to give you a biased estimate, or you might end up with a lucky sample. That estimate here is more robust. Anyway, considering our single test set, that 20% holdout data set we created earlier on, logit achieves AUC 82, and lasso, well, tiny little bit better, but the data is low dimensional. So overfitting shouldn't be that much of a problem, and hence the regularization should not give you that big an advantage. Grid searching, lasso, again, 823, 824. So a tiny little bit of improvement we gain when we carefully tune our penalty parameter. But if you really want to make a big jump, then you need random forest or HGB. So the takeaway here is that the data exhibits a strong signal. The feature to target relationship is very strong. And from the big difference between the linear and the nonlinear classifiers, you can conclude with confidence that the feature to target relationship exhibits nonlinearities, which all these models cannot pick up, but random forest and XGB, of course, they can pick up the nonlinearity or also interactions, which we did not model explicitly in our logit models and our linear models. So there are strong nonlinearities in the data, really calling for random forest or XGB or some other nonlinear model. We should try neural networks, which again, I did not incorporate, but it would be really easy because there is a class available in scikit-learn, and then a few lines of code. Try that as your homework. It's probably a good exercise. It's super easy, I promise. Okay, the last bit was the PDP. Permutation-based feature important is useful. Do you know which variables matter and how much? But you don't know in which direction they affect the target. So here, for instance, debt to income is the most important variable, but does that mean that higher values are associated with higher risk to be bad, or does it mean it's associated with less risk to be bad? And by the way, when saying higher risk to be or less risk to be bad, that's slightly inaccurate because it's about our model and how our model translates higher or lower value of that variable into predictions. But we don't see that. And this is where partial dependence is useful. The functionality is also in the namespace inspection. We import partial dependence, and then there is a convenient function, plot partial dependence. That's all you need to do. You tell it for which features you want to create a partial dependence plot. You again give it a classifier. The training data, I gave it the training data, but that's debatable. There are good reasons why you create a PDP for the training data, but there are also good reasons why you might want to create a PDP for the test set. It really depends on your goal of creating the PDP, which is more suitable. That's not so easy to say one is right, the other is wrong. And that's it. The rest is again some plotting, because we are creating PDPs for all the features, and hence you need to arrange your plots in some way. And maybe it was naive to Oh, it was definitely naive. To do that, yeah, classifier is not defined because I did not run the previous code for. That's easy to remedy. Since I now have overwritten my previous PDP, I need to run it and keep talking until the result pops up, which is slightly difficult because we are in the end of our notebook. But, well, to not waste your time and not waste my time, let me quickly jump ahead. I hope you remember what a PDP is supposed to look like. If not, okay, you'll see some shortly, but there is one thing. The PDP will give us a plot of the predicted response of your model against the values of one feature while marginalizing over all the other features. Getting there, getting there. Here we go. Here we go. We have the partial dependent for loan, more due, value, varies. That was an important variable. Let's have a look. The number of delinquent credit lines, number of times you have defaulted in the past. And here we see that if this grows, then the output of our model, our predictions also go up. And the point I wanted to make earlier is that what does that really mean here, this positive slope? And essentially what it means is that for one of the two classes, the probability increases when delinquent. The value in that variable increases. But you don't know, and unfortunately, the labeling of these convenience functions does not reveal which class is actually plotted here. In other words, do we see on the y-axis the model predicted probability of good or bad? And it changes everything. So it's important to know. Well, long story short, by default, you get not by default, the y-axis shows you the predicted probability for the positive class. Okay, super helpful. So what is the positive class? That is the class with the larger value in the data. And here, our target variable is Boolean. It's stored as false or true. That equals false or true. I'm illustrating that down here. If you look at the target variable and extract some values, it's stored as a Boolean. And if you convert that to a number, you'd find that true is translated to 1, false to 0. So 1 is the larger value. And hence, true is the positive class. So we do see P of bad. And that's something you must be aware of. What really do I see? Because otherwise you cannot make sense out of these graphs. So the probability of bad increases according to our model. These are predictions, not actuals. The probability of bad increases according to our model if the number of previous default events, let's say, delinquent credit lines increases. That makes sense. If you have done bad in the past, you will do bad in the future, sort of. That's what this says. And always watch these little rags down here that indicate where the mass of the data. So while the plot seems to tell a very strong signal, be careful, because these larger values here of your feature, delinquent, there is virtually no data on which you could really estimate reliably what your model is doing here. All the data sits here with delinquent equal to 0 or 1, right? So these regs are really important when interpreting the feature values. Let's look at one more. My favorite, debt to income. Debt to income. That's really interesting. Note that these numbers are scaled, right? I've scaled everything using the Z transformation. That's why we see a lot of data between minus 1.5 and, well, 1.5, say. And then we see if it gets too large, debt to income, if there's too much debt relative to the income, this is when the probability of that, according to our model, the predicted probability of that goes up noticeably. Whereas in a certain range, all is well. And again, that makes a lot of sense. This bump here, well, this bump, I cannot make sense of that. It's probably an artifact in our data. It's still a tiny data set, so you wouldn't expect too smooth your PDP. Overall, the trend makes a lot of sense. Right, and that really concludes our tutorial. We also get the PDPs for our dummy variables, and of course they are linear because these are dummies. And this is how we can diagnose the model. We saw before which features are important to our random forest, and here we see how does random forest employs these features. What values cause random forests to predict higher probabilities of being bad or lower? Here, for instance, CLH, right? The age of the oldest credit line, if that's a larger value, the age of the oldest credit line is large. So that's a long-term customer. And that makes sense. Long-term customers, our model predicts these to be less risky. Makes sense if you're a customer for a long time. Yeah, you are less likely to default on a loan. And this helps to create some confidence in the model that we can interpret certain variables and how the model translates variable values into forecasts, and seeing that for many variables these translation makes sense. That creates some confidence in our black box random forest, even if we do not have this nice linear relationship that we would have in a regression model. And that concludes our journey through Python machine learning. You have seen a lot, and as I said, I hope these examples will prove useful for you. Have a look through that tutorial, run things, and it's a lot of code, but the key bits are repetitive, and I'm very sure you'll get used to it very soon. And with that, I wish you a wonderful day ahead. We will meet again very soon for another tutorial, and the next on our list will be neural networks. We have introduced Python, we have revisited what we did in beds, and now we will move on with neural networks, starting with coding them manually, and then bit by bit move on to some deep learning libraries that make our life a little bit simpler, as scikit-learn makes our life simpler when it comes to ordinary supervised machine learning. All right, thank you very much. Hope you enjoy the notebook, and till very soon.